Thank you for your taking time out of your busy schedules to join us. I hope you had a good lunch break. Now, we are going to start the second half. We will do our best in the second half so as not to lose the first half where we learned a lot. The first part of the second half will be presented by myself, Ikko Ashimine. In my presentation, I'll introduce a new compiler called Codon that can speed up Python. Please stay with me until the end of the presentation. Here is the agenda for this presentation. In chapter 1, I'll give an introduction to this presentation. In chapter 2 is a light-hearted explanation of what Codon is. In chapter 3, we'll compare Codon with other acceleration methods. Chapter 4 will explain how to use Codon and show a short demo using Google Collaboratory. Chapter 5 will present the roadmap for Codon, and Chapter 6 will summarize this presentation. Chapter 1 Introduction. First of all, let me briefly introduce myself. My name is Ikko Ashimine. Please call me Ikko. I am an engineer living in Tokyo, Japan, and I have developed various web services, consumer games, and smartphone applications. I am currently a board member of iTechnology Company Limited. Recently, I am interested in artificial intelligence and how many opportunities to use Python. Here is my account on social networking sites. My account name is Ochen Eltshire, ELTOCIEAR. Here is the business card I use. Get a digital business card from QR code. Here is a brief explanation of Python. Python is simple and readable syntax, diverse libraries and frameworks, versatility, a strong community and support, wide range of applications. So Python is beautiful, but Python is very slow. Therefore, let's look at how to speed up the process. Chapter 2 about Codon. First of all, let me briefly explain about Codon. Codon is a Python accelerating compiler developed by MIT researchers since around 2021. A venture to promote Codon has also been started under the name Xloop. This is Xloop logo, Codon logo. Compiles Python code to native machine code without any runtime overhead. Speedups over vanilla Python are on the order of 10 to 1000 100 times or more. Supports native multithreading. Extensive via plugin infrastructure. Free of charge. Syntax. If you know Python, you already know 99% of Codon. But differences with Python. Codon's int is a 64-bit signed integer, whereas Python's after version 3 can be arbitrarily large. Codon currently uses ASCII strings, unlike Python's Unicode strings. Since Codon performs static type checking ahead of time, a few of Python's dynamic features are disallowed. For performance reasons, some numeric operations use C semantics rather than Python semantics, while most of the commonly used built-in modules have Codon native implementations. A few are not yet implemented. However, can still be used within Codon via from Python import. Chapter 3 Comparison with other CPython. Codon tries to follow CPython's syntax, semantics, and as closely as possible. Aside from new cases where Codon differs from CPython, for performance reasons, one example being Codon's 64-bit int vs CPython's arbitrary with int. Performance-wise, speedups over CPython are usually on the order of 10 to 100 times. Number. While Codon does offer a JIT decorator similar to numbers, Codon is in general an ahead-of-time compiler that compiles end-to-end programs to native code. It also supports compilations of a much broader set of Python constructs and libraries. PyPy. PyPy strives to effectively be a drop-in replacement for CPython, whereas Codon differs in a few places in order to eliminate any dynamic runtime or virtual machine and thereby attain much better performance. Python. Like Python, Codon has a Python extension build mode that compiles to Python extension modules, allowing Codon compiled code to be imported and called from plain Python. Chapter 4 Practical Examples and Demo. Before I get into the demonstration, let's first introduce the commands related to Codon. First, let's look at how to install Codon. In a terminal, such as macOS, you can use this command. I mainly use this command. In Google Collaboratory, the command to install Codon is here. In the short demo I will show you later, I will use this command. The command is prefixed with echo y to indicate yes or no when updating the path. In the Windows environment, the only way to build from source code, which can be found at this link. I apologize in advance, but I have never run Codon in Windows environments, so I will not introduce it here. Use Codon. Following the installation described earlier, this slide explains the execution commands of Codon. The execution command in a terminal such as macOS are shown here. The default compilation and execution mode is debug mode, but you can explicitly specify the debug mode by adding the -debug option. The release option can also be added to specify release mode, as shown here. This enables compilation and execution in an optimized state. This will be shown in the demo later. Here is the execution command at Google Collaboratory. In the short demo that follows, I run this command. Now, let's start a short demo using Google Collaboratory. First, I will install Codon using the installation command I introduced earlier. Please wait a moment. Yes, you can now use Codon. I have prepared some test code for you to use. Let's see how performance differs from normal Python, CPython. First, here is a test code for calculating prime numbers. The actual source code is shown here, which simply calculated and displays the prime numbers. I measure the time before and after the execution and determine the execution time. Now, let's run its normal Python. Please wait a moment. Mm, eh, okay, the process is complete. The execution time is 16.2 seconds. Next, let's run it in debug mode, which is default in Codon. Oh, processing is completed. Execute time is 1.3 seconds. At this point, you can see that the performance has increased by factor of 10. Next, let's run it debug release mode. Record completed execution time 1.1 seconds. Processing is about 0.21 seconds faster. Next is the test code for the Fibonacci sequence. The actual source code is shown here, which is also a simple calculation. As before, uh, let's run the CPython, where it takes a while. A little too long. This, I'm sorry. Uh, but if you don't set the value at this level, you won't be able to measure the execution time on the Codon. Please wait. Sorry. Uh, just a moment. Oh, completed. Execution time 46.2 seconds. Hmm. Uh, okay. Now, let's get back on track and run Codon in debug mode. What do you think? Oh, execution time is 0.8 seconds. The speed is over while mightily fast. Next, let's run it Codon release mode. Execution time is 0.4 seconds. The difference is even greater than in the previous prime number calculation test. The last comparison is done by executing the command function. The source code looks like this. Now, let's try this one in regular Python as well. Please wait a moment. Okay. 9.4 seconds This also takes quite a long time. Now let's try it with Codon. Ah, error card. But must comment out this line. Okay. Hmm. Execution time 0.3 seconds. Next, release mode. Hmm. This one takes 0.2 seconds. Again, even faster. Codon can be executed with the extension .codon. Here is a copy of a gamma function file from earlier, with the execution changed from .py to .codon. Now let's execute it with the codon command. Hmm. The execution time seems to be the same as in the case of .py. Next, release mode. Hmm. Same as. Now, let's look at the output of the executable files by the codon build command. Let's execute it with -o. The output uh, ACK is a an executable file. Hmm. Invisible, but exists. So let's execute it. Hmm. Okay. The execution time is almost the same as in the case of .py file. Oh, this column it can specify a file name with -o, outputs an executable file with exe, an object file with -obj for object files, and LLVM for LLVM files. And the release mode output. Yay, release mode files. Hmm, even faster. Okay, here. Then back to presentation. Roadmap. How else to show them? I'll adding this content to the slide later. In this chapter 5 roadmap, I will introduce the roadmap of Codon. Roadmap. Codon's goal is to be as close to CPython as possible while still being free statically compilable. While Codon already supports much of Python, there is still much to be done to fully realize its potential. Here is a high-level roadmap of the things we want to add, implement, or explore. Core features, type system improvements, first class types, and compile time metaclasses, full class member dedication, Implicit union types to support mixed type collections. Periodic type arguments using foo bar. Parallelism, async await support, multiprocessing support, automatic looking in parallel code. Example, if mutating a data structure shared between threads, race detection. Compatibility with Python 3.10 plus. Augmented separators slash n asterisk. Constructor object matching in the match statement. Support accessing various object properties, dict slots, etc. as much as possible in a static context. Beta error message, warning support, explain performance considerations, explain the CPython feature is not supported. Modules and incremental compilation, cache compilation modules, fast generics compilation in debug mode for quick slowdowns, memory management, auto-tune garbage collector, optional alternative memory management modes like reference counting, optional automatic switching between Codon and CPython, compile only compatible functions and leave the rest to Python. GPU support, target Apple, AMD, and Intel GPUs. GPU-specific compiler optimizations. Example, for using various Python constructs on the GPU. Interoperability with other languages. Direct C++ interoperability with CLang. R interoperability. Libraries. Currently, machine Python functionally can be easily accessed via a from Python import foo statement, which is sufficient in most cases as many libraries are just seen wrappers around the C libraries and are not performance sensitive. However, in the near future, we would like to support the following module natively. Python standard library, complete built-in support, one-to-one compatibility with existing Python functions and modules, file modules, OS, sys, struct, passlib, and so on. Pretty much everything else on an as-needed basis. Native NumPy, pandas, etc. having Codon native versions of the most popular third-party libraries would allow them to work with Codon's other features, like multi-threading and GPU. We are currently prioritizing NumPy and pandas with, but aim to later target all the popular libraries as well. Unicode support, Python's testing infrastructure and tools, Windows support, a same package manager similar to Rust's cargo, auto detection of installed Python libraries, improved CodonJet library support, better error messages, better installation flow, free static binary support like Go, remove Codon RT runtime library dependency if needed, remove libcpp dependency, improve Jupyter support, auto compilation and code inspection, Jupyter Magic command support, plugins for Visual Studio Code, Beam, Emacs, and so on. Documentation. Free document major differences with CPython. Document Codon IR API with guides and tutorials. Document all supported modules. Nice to have. Implement Codon in Codon. Chapter 6. Conclusion and Closing. This is how I would summarize this presentation. It can be compiled with few changes to regular Python. Codon is and will continue to be free of charge. Codon can run 10 to 100 times faster in JIT mode. Codon can output executables from source. Many more updates are planned for Codon. Thank you for listening to the end. If you have any questions, please send them to my email address. Please remove spaces and add to the text with questions from this conference. Enjoy the rest of the conference. See you later somewhere else.